You know, we're practically drowning in data these days. Every single click, every swipe, every purchase, it all just adds to this massive digital ocean. So in this explainer, we're not just going to learn how to swim in it, we're going to figure out how to harness its power. We're talking about big data analytics, finding that crystal clear signal inside all the noise. Let's dive right in.
So think about it, pretty much every organization out there is sitting on a mountain of data. But here's the million-dollar question you've got to ask. Is that mountain a priceless asset, like a gold mine, just waiting for you to find a treasure trove of insights? Or is it an avalanche just waiting to happen, about to bury you in sheer complexity?
And this quote, it's the key to everything we're talking about. I mean, think of raw data as just a giant pile of bricks. By itself, it's just a pile. But if you have the right blueprint, and that's what analytics is, you can build an absolute skyscraper. That's the transformation we're after, turning worthless data into priceless insight.
Now, to really get why we need these new tools, we first have to wrap our heads around the incredible scale of the problem. We're not just talking about a lot of information. We're facing a full-on data deluge. And trying to use the old tools, databases and spreadsheets, that's kind of like trying to empty the ocean with a teacup.
So, how do you know when your teacup is officially overflowing? Well, the warning signs are usually pretty clear. Is your data processing slowing down to a crawl? Are you having a tough time trying to integrate all the new, messy data types, like from social media feeds? Is the sheer speed of the data coming in just overwhelming your systems? If you're sitting there nodding your head, yeah, it's probably time to start thinking bigger.
Okay, so you've seen the problem. But here's the thing. Just going out and buying some fancy new technology isn't the solution. Nope, that's just an expense. To actually succeed, you need a plan. You need a blueprint for turning that data avalanche into a stable, seriously valuable asset.
You see, success in big data isn't really about the tech. It's about the strategy. Think of these as the pillars holding up your entire project. First, you absolutely need a clear business goal. What problem are you actually trying to solve? Next, you need a strong executive sponsor, someone who can clear the path for you. And maybe most importantly, you need a company culture that trusts data over gut feelings. Without these pillars, even the coolest technology is just going to fall flat. But look, it's not always going to be a walk in the park. You're going to face some hurdles. For one, there's the massive volume of data itself. Then you've got the challenge of integrating all these different messy data types. You also have to think about security and governance. Can't forget that. And of course, you've got to find the people with the right skills and the budget to make it all happen. But you know what? Knowing these challenges exist is half the battle won.
All right, now for the really exciting part. Let's talk about the tech powerhouses, the actual tools of the trade that make all of this big data analytics stuff possible.
First up, we have Hadoop, the original workhorse of big data. Its core idea was honestly revolutionary. It was basically, why use one super expensive supercomputer when you can link together a whole team of cheaper ones? Hadoop connects clusters of what we call commodity hardware. We're just talking about standard, off-the-shelf computers, and gets them to work together in parallel, each one tackling a small piece of a giant problem at the same time. So how does it coordinate all those different computers? Well, through a clever process called MapReduce. Here's a really simple way to think about it. Imagine you have a gigantic pile of colored Lego bricks, and you need to count them. The map step is like giving a handful of those bricks to a bunch of different people and just telling them, hey, sort these by color. The shuffle and sort step is when they all bring their little sorted piles together. All the reds go in one big pile, all the blues in another. And finally, reduce is when one person just counts the total number of bricks in each big color-coded pile. That's it. It turns a huge, impossible task into a bunch of small, totally manageable ones.
But what if you need an answer like right now? Well, that's where Spark comes in. It's the in-memory speedster. The key difference here is that Spark does all its work in the computer's super fast memory, its RAM, instead of constantly having to read and write from a slower hard disk like Hadoop does. And that one change makes it dramatically faster for a lot of jobs.
So really, it just comes down to picking the right tool for the job. Spark is all about speed, using that fast but more expensive memory. Hadoop, on the other hand, is about cost-effective power, using slower but much, much cheaper disk storage. It's kind of like the difference between a race car and a freight train. Both are incredibly powerful, but you definitely wouldn't use them for the same task. Okay, let's get really practical. You're probably going to lean towards Hadoop when you've got massive data sets that are way bigger than your available memory, or for batch processing jobs that aren't super time sensitive and you want to keep costs down. You'd choose Spark for things like real-time stream analysis, for complex machine learning jobs, or really any situation where getting results back quickly is your #1 priority.
And that need for speed brings us to a really cool, kind of radical new idea. What if you could analyze data not after it's been sitting in a database, but in the exact moment it's being created? We're talking about data in motion.
This is called stream analytics, and it's a total game changer. Think of it like this. Traditional analytics is like taking a photograph and then studying it later to see what happened. Stream analytics, on the other hand, is like watching a live video feed and being able to react instantly to what you're seeing. We're not just historians of our data anymore, we're active participants in a live event.
So, where do you actually see this in the real world? Well, think about your favorite online store. Every click you make, every page you look at, every search, it's all part of a live data stream. Companies analyze that stream in real time to give you personalized recommendations and special offers while you're still on the site, turning casual window shoppers into actual buyers.
Or how about this one? Cybersecurity. A big company can't wait hours or even minutes for a report to find out it's under attack. By analyzing network activity as a continuous stream, security teams can spot and stop cyber attacks the moment they start, not long after the damage has already been done.
And this shows just how much stream analytics can impact the physical world. Power companies analyze streaming data from millions of smart meters to get a live, up-to-the-second view of the entire electrical grid. This lets them predict demand, prevent outages, and manage power way more efficiently. They can respond to something like a heat wave or a cold snap in real time.
So we've gone from the chaos of the data deluge all the way to the clarity of real-time insight. It really proves that the challenge isn't just about having the data, it's about having the right tools and the right strategies to make sense of it all and to do it fast. Which kind of leaves us with one final thought. Your data is generating insights every single second. The real question is, are you fast enough to listen?
Welcome back to the deep dive. Today, we are plunging, well, deep into the engine room of the digital economy, big data analytics. For years, we've all heard about the 3 V's, volume, velocity, and variety. But our source material really hammers home a crucial point, those V's. They're just abstract concepts unless they deliver actual quantifiable business utility. Yeah, the core idea that's driving this whole deep dive today is that big data itself, doesn't matter how vast or fast it is, it's fundamentally, worthless unless you have the analytical power and the organizational setup to turn that raw stuff into real value. We're really talking about big analytics. We've got a stack of material here. Covers everything from the architectural basics of big data, the non-technical things, the critical success factors that make or break these projects, and detailed comparisons of the big processing frameworks. Hadoop, Spark, and increasingly vital stream analytics. Our mission today. Cut through the noise, the buzzwords, and pull out the really critical knowledge. We want to show you the specific signs that tell you when your old systems are actually breaking down. And importantly, the real operational differences between these new technologies so you, the listener, can figure out which tool fits which job. Okay, let's unpack this. Because the shift we're seeing, it's not just like an upgrade. It's a whole new way of thinking, moving from just running canned reports on neat structured data to enabling real, deep, on-demand exploration of all the data an organization might have.
That's absolutely the right place to start. The old limitations, the traditional relational systems, it wasn't just that they were complex, it was about what they couldn't include. Often, the analysis tools were too tricky for the average business user, sure. But more fundamentally, the data repositories themselves, they just didn't contain everything people needed. They couldn't handle unstructured stuff, social media feeds, sensor logs, that kind of thing. This whole big data analytics paradigm, it's the disruptive force that lets us finally ingest everything and analyze it, often right away.
Right. But before any company dives headfirst into a massive big data project, they need more than just a feeling it's the right thing to do. They need a solid, probably financial justification. Our sources lay out 5 key litmus tests. These are the specific signals that show you've hit that tipping point. If an organization answers yes to any one of these 5, honestly, they're probably already behind the curve and need to get moving on this, like yesterday.
And what's fascinating here is how these aren't just abstract data problems. They really pinpoint the exact ways the old guard, the RDBMSs, the relational database management systems fail. So test number 1 is pure scale, volume limitation, simple as that. If your current systems, your analytics platforms, just cannot physically process the amount of data you're generating or the amount you want to analyze, maybe a report that took 3 hours now drags on for 30, you've hit the wall. Your analysis is bottlenecked.
And that volume issue often ties right into the second one, which is about the messy nature of modern info. Test 2, the variety-fidelity conflict. Businesses today need to pull in all sorts of new data sources, right? Social media chatter, RFID tags constantly pinging, sensors spitting out readings every millisecond, web logs, messy text data, GPS points, you name it. The problem is trying to cram all that inherently non-relational, multi-structured data into a rigid, predefined row and column structure. It means you inevitably sacrifice the richness, the fidelity of that original data. You're basically forcing a square peg into a round hole, a relational round hole.
Exactly. And that loss of fidelity can be a huge problem, especially if you're doing things like predictive modeling. You need the original nuance. The third indicator brings in time, the velocity integration need. It's not just how much data, but how fast you need it put together. If you need to integrate data incredibly quickly to keep your analysis current maybe within minutes or hours, and your existing systems rely on those old multi-day ETL cycles, extract, transform, load, well, then your decisions are being made on stale data, potentially completely irrelevant information.
And that speed of integration points directly at the sort of architectural inflexibility of the old model. Indicator 4 deals with schema rigidity. This is probably the most fundamental constraint of a traditional RDBMSS. You have to define everything up front. Your columns, your rows, the data types, the whole structure of the schema, long before any data actually shows up. This often means weeks, maybe months of expensive, brittle ETL development before analysts can even start looking at the data. But with big data, especially when you're just exploring, you might not even know the nature of the information yet. Or maybe your development cycles are just so fast you can't wait weeks to define the perfect schema. You need what the sources call a schema on-demand approach, the ability to figure out the structure when you query the data, not when you load it in. That shift fundamentally changes how you manage and analyze data. It's huge.
And the last one, number 5, it loops back to speed, but this time it's about sheer arrival rate. Data speed. If data is just hitting your organization system so fast, streaming in from maybe millions of devices at once, that your traditional platform literally cannot keep up with the intake velocity, then you're not just falling behind. You're actively losing opportunities, maybe missing fraud, risking compliance failures, all in real time. This is the clearest sign. It marks that necessary jump from thinking about structured data at rest in neat databases to wrestling with unknown, messy, multi-structured data that's arriving at, frankly, breakneck speed and demands immediate attention.
Okay, so we've got it. The tech itself, the traditional stuff, it physically breaks under modern data pressure. Volume, variety, velocity, it just can't cope. But, the sources are pretty clear that the hardest part often isn't buying faster servers or bigger storage arrays. It's the people. The organization, understanding the tech Hadoop, Spark, whatever, that's only half the battle. Our sources really stress that success with big data analytics depends just as much, maybe even more, on organizational alignment, on the company culture. Why doesn't just buying a ton of new hardware solve the data problem if the culture isn't ready? Here's where it gets really interesting.
Because you can buy technology off the shelf.
Okay.
Cultural change. That has to be earned. It takes continuous effort, leadership commitment, the 8 critical success factors, the CSFs that are laid out in the source material. The first 4 are almost entirely about the non-technical strategic stuff.
Number 1, and this has to be the starting point always, a clear business need. Simple, right? Investments have got to align directly with what the organization is trying to achieve, its vision, its strategy, whether that's strategic growth or tactical market adjustments or just making operations more efficient. If you're just investing because the tech is cool, you're setting yourself up for an expensive science experiment that probably won't impact the bottom line.
Absolutely. And right behind that, factor number 2, strong, committed sponsorship. This is crucial. If the goal is real, enterprise-wide transformation and big data initiatives often are, the sponsorship has to come from the very top. C-suite level. It's just incredibly difficult, maybe impossible to pull off these big projects without a highly visible, genuinely committed executive champion who's pushing for it, fighting for resources, and breaking down those inevitable organizational roadblocks.
And number 3, alignment between business and IT strategy. This sounds like a no-brainer, but it's amazing how often it gets messed up. Analytics needs to be seen as the enabler of the business strategy. IT is there to make the business goals happen, technically. It shouldn't be the other way around, where IT drives strategy based on some new software they want to play with. Priorities have to flow from the business needs, supported by data capabilities.
Then we hit number 4, and this is often where the real cultural friction happens. Fostering a fact-based decision-making culture. This means consciously moving away from relying purely on intuition, gut feelings, or just how we've always done things. It's about letting the evidence, the actual numbers, drive the decisions.
Okay, but that sounds great on paper, in a meeting room. Isn't it incredibly tough, maybe even politically risky, to ask a senior exec, someone who built their career on sharp instincts, to suddenly ditch their gut feel for a dashboard they might not fully understand or trust yet? How does senior management actually make this shift happen?
It really requires clear, decisive action from leadership. Senior managers have to be vocal cheerleaders for this change. They need to actively stress that the old, intuition-only ways are being phased out, starting now. And probably the most powerful tool, accountability. They have to ask to see the data, the analytics that supported every major decision. Show me the numbers. The sources are really clear on this. Linking incentives, maybe compensation, directly to these fact-based behaviors. That's the fastest way to get everyone on board and accelerate that cultural change.
Makes sense. Tie it to the wallet. Okay, factor 5 is about the infrastructure itself. A strong data infrastructure. Old analytics relied heavily on data warehouses, right? But success now means you have to marry that established, mature infrastructure with all these new big data technologies. You need a kind of holistic, synergistic setup that keeps the best parts of the old governance, reliability, but enhances it with the scale and variety handling of the new tools.
Exactly. And the last three CSFs are kind of foundational elements, but often they turn out to be major bottlenecks in practice. You need the right analytics tools for the job.
Yeah.
You absolutely need personnel with those advanced analytical skills, the data scientists, the engineers, and you need to constantly maintain and evolve that strong hybrid data infrastructure. It's not a one-time build.
Okay, so even if you understand these success factors, companies still run into major hurdles trying to implement this stuff. What are the big operational challenges that typically trip organizations up in the real world?
Well, the list usually starts with just the raw data volume challenge. How do you capture, store, and process petabytes, maybe exabytes, of data quickly enough? Making sure the right information is actually available when someone needs to make a decision, not 3 weeks after the fact. Then there's data integration. It's really hard and often expensive to quickly combine data that's fundamental, different structures, different sources, especially when some of it is streaming in constantly. And as that volume, variety, and velocity just keep growing, data governance becomes exponentially more complex. Organizations really struggle to keep up with security rules, privacy regulations, figuring out data ownership, maintaining data quality across systems that are constantly morphing and expanding.
I noticed one challenge called out in the sources that seems like a perfect pivot to talking about stream processing later. Processing capabilities. The material says that to get the most value, data often needs to be analyzed, like the instant it's captured, or even while it's being captured. That need for immediate processing, that seems to be what really pushed the industry beyond just batch analysis, right?
Precisely. That's the driver for things like Spark and stream analytics. And we absolutely cannot forget the people problem. Skills availability. There's a huge global shortage of these new kinds of experts, the data scientists, people who have that rare mix of stats knowledge, analytical thinking, and the distributed computing skills needed to actually use these powerful tools effectively. And finally, with all this new tech and experimentation, you've got to manage the solution cost. Making sure there's a positive ROI often means doing pilot projects, experimentation, and discovery work first to reduce the risk of investing heavily in something that doesn't ultimately deliver value.
So to actually tackle these massive computational hurdles that big data throws up, the industry came up with some really innovative techniques. They fall under the umbrella of high-performance computing, or HPC. These are basically designed to smash through bottlenecks and keep up with those extreme data demands.
Yeah, these techniques are all about getting insights faster, mostly by moving the processing closer to the data or making the processing itself way faster. The first big one is in-memory analytics. This is a game changer. Instead of constantly reading data from relatively slow disk drives and writing results back, which involves a lot of time-consuming I/O, you load the big data and do the analytical calculations entirely in the computer's main memory, in RAM, and you distribute this across a cluster of powerful machines, or nodes. This lets you solve really complex problems almost in real time because you skip that slow disk I/O step.
Okay, RAM is fast. What else? There's also in-database analytics. How does that work?
Right. Instead of the old way exporting massive data sets out of the database, moving them across the network, maybe converting them in different formats multiple times, you perform the data integration steps and the actual analytic functions inside the database environment itself. This cuts down the time to insight dramatically. And it also helps with governance because the data doesn't leave that controlled environment as much. Less data movement, fewer copies.
And then there are more hardware-focused approaches.
Yep. Particularly grid computing, which is about efficiency through sharing. It lets analytical jobs run on a shared, Centrally managed pool of IT resources could be servers, storage, whatever, makes better use of the hardware you have. And then specialized appliances. These are basically pre-packaged boxes or racks of tightly integrated hardware and software servers, storage, networking, analytics software, all bundled together and optimized for speed and scalability. You buy it as a unit specifically designed for heavy-duty analytics.
Okay, so the industry clearly built some serious machinery to handle this stuff, specialized, powerful infrastructure. But again, it always comes back to the why. Why go to all this trouble, all this computational expense? What's the real measurable business impact that justifies these huge investments in tech and skills?
Well, if you look across industries, the top two business problems that big data analytics consistently tackles are pretty clear. Number one, achieving process efficiency and cost reduction, and number two, dramatically enhancing customer experience. Those two benefits are almost always the main drivers for investment.
But the emphasis definitely shifts depending on the industry, right? Our sources point out that for heavy industry and government sectors, think manufacturing, government agencies, energy, utilities, transportation, even healthcare process efficiency and cost reduction are usually the absolute top priority. They're focused on optimization, predicting machine failures, cutting waste.
Exactly. But then you look at highly customer-focused industries, like insurance or retail. For them, enhancing that customer experience usually jumps to the top, using big data for deep personalization, predicting what customers want next, anticipating churn, and trying to prevent it.
And we can't forget risk. For banks, financial institutions, and also the education sector, which apparently faces big challenges with fraud and security, risk management is often cited as the #1 driver. Using big data analytics for things like real-time fraud detection, cybersecurity threat analysis, ensuring regulatory compliance.
Yeah, and the full list of impacts just shows how pervasive this tech is becoming across all business functions. We're talking concrete results like maximizing revenue, doing much more targeted cross-selling and upselling, identifying customers about to leave much faster, improving customer service response times, finding new product opportunities more quickly, handling complex regulatory requirements, and seriously boosting security capabilities everywhere.
All right, let's shift gears now and get into the actual tools, the foundational technologies that made a lot of this possible. It's worth remembering those shared characteristics of these emerging big data techs. They all kind of reject the old, expensive, monolithic mainframe model. Instead, they use cheap, standard commodity hardware that you can scale out just by adding more machines in parallel. They use non-relational storage specifically designed to handle messy, unstructured, or semi-structured data, and they rely on advanced analytics and visualization tools to actually make sense of what comes out of all that processing.
And the technology that really kicked off this whole revolution, the one everyone first thinks of, is Hadoop. Hadoop is that open source framework. It was built specifically for processing, storing, and analyzing truly massive amounts of distributed, often unstructured data. It was directly inspired by a paper Google published about a function they called MapReduce, and it was designed from the ground up to handle data measured in petabytes, even exabytes, spread across potentially thousands of relatively inexpensive computers all working together.
And the core idea, that conceptual breakthrough, was parallel processing using the scale-out approach, right? Instead of one giant, super expensive specialized computer, Hadoop breaks the big data problem into lots of smaller pieces. Then each piece gets processed at the same time across this whole cluster of cheap, standard servers.
Exactly. And to really grasp how it works, you need to look at the architecture. When you want to process some data, it first gets broken into these smaller parts or blocks. And these blocks are loaded into the Hadoop Distributed File System, HDFS. HDFS is the storage layer, the foundation. And it's brilliant for unstructured and semi-structured data precisely because it doesn't demand that data fit into neat, predefined rows and columns like a relational database does.
Okay, but you're building this system on potentially unreliable, cheap hardware. What stops data from just vanishing if one of those commodity servers fails? Which they probably do fairly often.
That's where the built-in fault tolerance comes in. It's really clever. Each block of data isn't just stored once. It's automatically replicated multiple times, usually 3 times by default, across different servers, different racks even, within the cluster. So if a node goes down, and yeah, they do fail, the system already knows where other copies of that data live. The processing just gets rerouted automatically. There's a master server called the name node that acts like the traffic cop. It keeps track of where all the data blocks are, which nodes are healthy, which have failed, and manages that whole replication process to ensure data integrity, even when individual machines die.
Right, so the data is safely stored and replicated across the cluster in HDFS. Then how does the actual processing happen? That's the MapReduce part.
Exactly. MapReduce is the processing engine. And this is often a point of confusion, so let's be clear. MapReduce is a programming model. It's not a specific language like Java or Python. Google pioneered it for distributing computation across their massive clusters. And its real genius is that it hides all the underlying complexity, managing the network communication between nodes, handling node failures gracefully, coordinating everything. The programmer just needs to write the logic for two specific functions, the map function and the reduce function. MapReduce takes care of running it reliably across the whole cluster.
Okay, let's try that colored square counter example from the source material to make it concrete. Sounds simple. Imagine we have a massive input, maybe terabytes of files containing images of colored squares, millions and millions of them. And the goal is just to count how many squares of each color, red, blue, green, etc., there are in total across all the files.
Okay, so MapReduce first takes that massive input folder and automatically splits it into many smaller chunks. Let's say we have a 1,000-node cluster. Maybe it creates 1,000 input splits. Then the map function runs in parallel on each of those 1,000 nodes, working on its assigned input split.
And the map function's job is what exactly? Just counting the colors it sees locally?
Sort of. The map function processes its local input chunk and typically transforms or emits key value pairs. In this case, it would read its square images, and for each square, it would output a pair like color 1. So it might output red 1, blue 1, red 1, green 1, and so on. The crucial thing here is data locality. The map task runs on the same node where its input data block resides in HDFS whenever possible. This avoids moving huge amounts of data across the network, which is usually the biggest bottleneck in distributed systems. Processing goes to the data.
Okay, so now we have 1,000 nodes, each having processed its little chunk and generated a list of color 1 pairs. What happens next? How do we get the total count?
Now comes the shuffle and sort phase, which MapReduce handles automatically. The system gathers all the key value pairs emitted by all the map tasks across the entire cluster. It then sorts these pairs by key, the color in our example, and groups them together. So all the red 1 pairs from all nodes end up together, all the blue 1 pairs end up together, and so on. These grouped values are then sent to the reduce tasks.
Got it. So all the red counts are now in one place, all the blue counts in another, then the reduce function steps in.
Precisely. The reduce function takes each key, each color, along with its associated list of values, a long list of ones in this simple case. Its job is just to perform the final aggregation. Here, it would simply sum up all the ones for each color to get the final frequency count. So one reduce task might output red 5,234,101, another blue 4,872,550, etc. And that's your final result.
That parallel procedural approach. You can see how it's powerful for things that aren't easy in standard SQL, like indexing the entire web, analyzing complex social networks, deep text mining, or prepping massive data sets for machine learning. Tasks that would just cripple a traditional database.
Exactly. It's designed for those kinds of large-scale, batch-oriented analytical tasks.
Wait a minute, though. Let's challenge that architecture again. You said HDFS is a file system, right? Not a DBMS. And it lacks indexing. So if I need to find one specific piece of information, say one transaction record or one user profile, and there's no index, doesn't that mean I have to run MapReduce and scan the entire petabyte data set every single time I need to look something up? That sounds incredibly slow for quick lookups.
That's a fantastic question, and it highlights a core trade-off and a common misconception. You're right, HDFS itself doesn't provide the kind of low-latency, indexed lookups you get in a traditional RDBMS or even many NoSQL databases. MapReduce is designed for full dataset scans for batch processing. If your primary need is to frequently fetch individual records very quickly, raw HDFS with MapReduce is not the right tool for that specific job. Its speed comes from massive parallel processing of the entire dataset, not from quickly finding one needle in a haystack.
Okay, that clarifies the limitation. It's built for batch analytics, not random access.
Yeah.
So Hadoop is clearly more than just HDFS and MapReduce. It's this whole ecosystem. What other key tools are usually part of the stack?
Yeah, it's definitely an ecosystem. Several important tools grew up around the core to make it more usable. A really key one is Hive. Apache Hive provides a data warehousing layer on top of Hadoop. Crucially, it offers a SQL-like query language called HiveQL. This was huge because it allowed people already skilled in SQL, which is a massive group, to interact with data in Hadoop without having to write complex Java MapReduce code.
So Hive makes Hadoop feel a bit more like a traditional data warehouse query-wise.
Exactly. And then there's Pig, initially from Yahoo. Pig provides a higher-level scripting language, Pig Latin, that's particularly good for defining complex multi-step data transformation pipelines. Think of really long, sequential ETL-like processes. Pig can sometimes express those more easily than HiveQL or raw MapReduce.
Okay, Hive for SQL-like queries, Pig for data flow scripting. What about that random access problem we just talked about?
Ah, that's where HBase comes in. Apache HBase is a popular NoSQL database, specifically a column family store, that is often run on top of HDFS. HBase is designed for very fast, real-time read-write access to specific rows or pieces of data within massive datasets. It provides those low-latency lookups and updates that raw HDFS and MapReduce lack. So you often see HBase used alongside Hadoop for applications needing both large-scale batch analytics and quick transactional access.
Okay, so Hadoop, with its ecosystem, really opened the door. It gave companies a cost-effective way to tackle huge amounts of unstructured data they just couldn't touch before. It let them analyze all the relevant data, not just small, potentially biased samples. And being open source, the initial software cost was low, which helped drive adoption.
Definitely. But it wasn't perfect, especially in the early days. The downsides were real. A big one was expertise. Hadoop is complex. It's constantly evolving. You need specialized skills to run it effectively, and there's still a significant shortage of experienced Hadoop developers and data scientists. That's a major bottleneck. But the biggest technical limitation, the one that really spurred the next wave of innovation, was its fundamental nature. Hadoop, using MapReduce, is primarily a batch-oriented framework. It excels at reading huge chunks of data from disk, processing them, and writing huge chunks of results back to disk. It was not designed for and isn't good at real-time processing or interactive analysis.
Right. And let's quickly recap those key myth-busting facts from the sources, just to make sure everyone's clear. 1. Hadoop isn't one single thing. It's an ecosystem with HDFS, MapReduce, Hive, Pig, HBase, etc., often packaged by vendors for easier enterprise use. 2. HDFS is a file system, great for storing huge files, but it's not a database management system, DBMS, in the traditional sense. No indexes, no standard SQL directly on HDFS. And 3, critically, Hadoop usually complements the existing data warehouse. It rarely replaces it entirely. It handles the messy, multi-structured data that the traditional DW struggles with.
Exactly. And that batch limitation, that slowness for certain types of jobs, led directly to the rise of Apache Spark. Spark is another open-source cluster computing framework, but it was developed specifically to overcome Hadoop's performance limitations, especially for iterative algorithms and interactive queries.
Okay, so if Hadoop MapReduce relies heavily on reading and writing to disk between steps, what's Spark's secret sauce? How does it achieve that speed?
The absolute key differentiator is in-memory processing. Performance. Spark is often cited as being 10x, even 100x faster than Hadoop MapReduce for certain workloads. Why? Because instead of writing intermediate results of computations back to slow disk drives, Spark tries to keep as much data as possible cached in RAM across the cluster nodes. It uses resilient distributed datasets, RDDs, which can live in memory.
So imagine you're running a machine learning algorithm that has, say, 20 iterative steps.
Right. With Hadoop MapReduce, each of those 20 steps might involve reading data from HDFS, doing some computation, and writing the intermediate results back to HDFS. That's 20 slow disk read-write cycles. Spark, on the other hand, would load the data into memory once, and then perform all 20 steps by accessing the data directly from RAM, which is orders of magnitude faster than accessing disk. This makes Spark a much more versatile engine. It can efficiently handle SQL queries via Spark SQL, streaming data analysis, Spark streaming, machine learning, MLlib, and graph processing, GraphX, all within one unified framework, and generally much faster than the older Hadoop batch model.
But that speed must come at a price, right? If Hadoop's the reliable, cheap workhorse that uses disk, Spark sounds like the race car incredibly fast, but needing premium fuel, maybe?
That's a pretty good analogy. The trade-off is largely cost, specifically hardware cost. Hadoop can run effectively on clusters with lots of relatively cheap disk storage because it's designed around disk I/O. Spark's performance relies heavily on having enough RAM across the cluster to hold the data it's actively working on. RAM is significantly more expensive than disk storage, so building and running a Spark cluster capable of handling very large data sets entirely in memory can be considerably more expensive from a hardware perspective.
So how does an organization choose? When is that extra speed worth the extra cost? It must come down to the specific job you need to do.
Absolutely. The use case is king here. The sources give good guidelines. You should probably stick with Hadoop, MapReduce HDFS when your total data size is just way too big to fit into the available RAM of your cluster. Your budget for hardware is severely limited. Your processing jobs are fundamentally batch-oriented anyway, like nightly ETL, and don't need real-time speed. Or you're mainly analyzing historical or archive data where speed isn't the primary concern.
Okay, that makes sense. Use the cheaper option when speed isn't critical or memory is the constraint.
Right. Conversely, you should definitely lean towards Spark when you absolutely need quick results, especially for interactive queries or iterative computations. You're running algorithms that involve many steps on the same data, like most machine learning. You need to analyze streaming data in real time or near real time, or specifically for machine learning tasks, because Spark's MLlib library is built to leverage that in-memory speed for iterative training.
Got it. Choose the tool based on the need for speed and iteration versus raw batch throughput and cost. Now, where does NoSQL fit into this picture? We mentioned HBase runs on Hadoop, but NoSQL is a broader category.
Right, NoSQL databases emerged around the same time as Hadoop, also driven by the need to handle large volumes of varied data structures, particularly for web-scale applications. But their primary focus is usually different from Hadoop's batch analytics focus or Spark's fast analytics focus. NoSQL databases are often optimized for serving up discrete pieces of data very, very quickly with low latency. Think about fetching a user profile for a website, retrieving product information for an e-commerce page, or storing session data for millions of concurrent users. They excel at these kinds of high-velocity, relatively simple read-write operations needed by applications.
So they're more about operational data access for applications rather than deep, complex analytics.
Generally, yes, although some NoSQL databases are adding more analytical capabilities. They often work with Hadoop and Spark. For instance, you might do heavy batch processing in Hadoop Spark and then load the results into a NoSQL database like HBase or Cassandra so that your web application can access those results very quickly. But there's that critical trade-off we need to highlight again, the one mentioned in the source material. Many NoSQL databases achieve their incredible speed and scalability by relaxing the strict ACT compliance guarantees found in traditional relational databases.
Right, ACD. Let's break that down again because it's important. Atomicity, consistency, isolation, durability.
Exactly. Consistency, for example, means that every transaction brings the database from one valid state to another, and everyone reading the database sees the same consistent picture. Durability means once a transaction is successfully committed, it will survive permanently, even if the system crashes immediately after. Relational databases go to great lengths to guarantee these properties, which is crucial for things like financial transactions.
But NoSQL systems often trade some of that safety for speed?
Many do, yes. It's often referred to as eventual consistency. To achieve massive scale and low latency across many distributed nodes, they might allow temporary inconsistencies. For example, if you update your profile picture on a social media site, it might take a few seconds for all your friends worldwide to see the new picture. The system is eventually consistent, but not instantaneously, strictly consistent everywhere. That's often an acceptable trade-off for performance in that context. But you wouldn't want your bank balance to be only eventually consistent. So NoSQL often involves consciously trading some degree of transactional integrity for significant gains in performance and scalability.
Okay, we've wrestled with volume Hadoop handling massive scale and variety non-relational systems like HDFS and NoSQL handling messy data. We've seen Spark tackle the need for faster analytical processing. But now let's hit the third V head-on, velocity, the sheer speed at which data arrives. This seems to pose the most unique challenge because the window to act on that incoming data can be incredibly short, maybe milliseconds.
It really does force a fundamental shift. The old store everything first, analyze it later approach just breaks down when data is flying in constantly. Our ability to generate digital information is now vastly outpacing our ability or even economic feasibility to store absolutely everything indefinitely. More importantly, for many applications, analyzing data that's already minutes or hours old means the insights are too late. The opportunity is gone or the threat has already materialized. Decisions based on old data can be worse than useless. They can be actively harmful.
So the driver for stream analytics is this need to spot important patterns or anomalies in that rapidly flowing data within a very tight time frame.
Precisely. Stream analytics, sometimes called data in motion analytics or real-time data analytics, is all about extracting actionable information from data as it flows, continuously. Think of the data not as a static lake, like in a data warehouse, but as a constantly flowing river, a stream. A stream is just a continuous sequence of data records, often called tuples. The analysis usually happens over a window of data, maybe the last 5 seconds of sensor readings or the last 100 clicks on a website. It's a finite, continuously updating subset of the stream. This capability is becoming essential because in many domains, the value of data decays incredibly rapidly. Time to action is shrinking.
Let's make this real with some applications. The sources highlight areas where this instant insight is absolutely critical, starting with the energy industry and smart grids.
Oh, smart grids are a perfect high-stakes example. You've got multiple continuous data streams pouring in real-time readings from potentially millions of smart meters in homes and businesses, data from sensors on generation equipment, wind turbines, solar panels, transmission lines, plus external data like weather models predicting wind speed or cloud cover. Now imagine a sudden, localized event. Maybe a severe thunderstorm pops up quickly. You could get simultaneous spikes in energy demand data from tens of thousands of smart meters in that area as people turn on lights and AC, combined with maybe a sudden drop in solar generation readings, all happening within seconds.
Wow, okay, no traditional batch system could possibly react to that in time.
Not a chance. Stream analytics engines have to ingest that burst of data instantly, correlate the demand spikes with the generation drops, maybe factor in the predicted storm path, and detect anomalies or potential overload situations in real time. This allows the utility operators to make immediate, critical decisions. Maybe reroute power, adjust generation from other sources like natural gas plants, maybe even trigger dynamic pricing adjustments to incentivize reduced consumption in the affected area, all to maintain grid stability and prevent cascading blackouts. The value here is reliability, safety, and efficiency measured in real time.
Okay, moving from critical infrastructure to commerce. E-commerce. The goal there is simpler, maybe, but still relies on speed. Turn clicks into cash, turn browsers into buyers.
Exactly. Think about major online retailers. Every single action you take on their site, every click, every page you visit, how far you scroll down a page, every search term you type is potentially being captured and analyzed as it happens. Sophisticated stream analytics platforms are crunching this data instantly, often combining your real-time actions with your historical purchase data, maybe data about what similar users are doing right now.
What are they trying to figure out from that stream?
They're trying to understand your intent in real time. Are you just browsing, or are you close to making a purchase? Are you confused? Are you comparing prices? Based on that instantaneous analysis, maybe they see you hesitating on the checkout button, or you keep scrolling back and forth between two products. They can trigger personalized interventions before you leave the site. This could be a targeted discount offer just for you, a bundle suggestion. Maybe a proactive chat window pops up, offering help. The goal is to nudge you towards conversion in that very moment, because if you navigate away, the chance of getting you back drops significantly. A delay of even a few seconds can mean a lost sale.
Fascinating. And the sources also mention high-stakes uses in telecoms and security. How does stream analytics play out there? In telecom, it's often about preventing churn, right? Stopping customers from leaving.
Yes, churn is a huge issue for telcos. They can use stream analytics by combining traditional data like call detail records, CDRs, who called whom, for how long, with potentially less structured real-time data like social media sentiment analysis related to their brand or services. The analytics engines can then work in real time to identify networks of callers. Who influences whom? Who are the leaders and followers within social calling circles? By spotting patterns, maybe negative sentiment starts spreading within a particular network, or a key influencer in a group stops using services. The company gets an early warning of potential group churn. They can then proactively target interventions, maybe special offers or customer service outreach towards those key influencers or the affected network, trying to manage perception and prevent a larger exodus.
And finally, law enforcement and cybersecurity. Seems like the potential here is enormous, maybe even a bit scary.
The potential is definitely massive, and raises important ethical questions too, of course. But from a technical perspective, streams of big data offer unprecedented capabilities for security. Think real-time situational awareness by combining feeds from traffic cameras, sensors, drone footage, social media monitoring, high-speed facial recognition against watch lists as people move through public spaces, analyzing network traffic patterns for cyber attacks. For enterprises, stream analytics apply to network logs, server performance metrics. Firewall activity is absolutely essential now for modern cybersecurity. It allows them to detect intrusions, denial of service attacks, malware propagation, or even malicious insider activity as it's happening, not hours or days later when the damage is done. It enables real-time defense against threats that can evolve incredibly quickly. If we just take a step back for a moment and connect all this powerful technology, Hadoop, Spark, stream analytics, back to the bigger picture, its application goes way beyond just making money or catching bad guys. There's been this really significant and frankly, quite inspiring growth in initiatives, often grouped under the banner of data for good,
Right, I've heard that term. It's really encouraging. These projects use largely the same tools and techniques we've been discussing, often leveraging publicly available data, but their goal isn't profit. It's about tackling really meaningful social and environmental problems, things affecting huge numbers of people, vulnerable groups, or the health of the planet itself.
Exactly. The focus is very much on humanitarian issues. Things like mapping poverty more accurately, tracking disease outbreaks, advocating for human rights, improving educational outcomes, understanding and mitigating environmental damage. There are some amazing organizations leading this charge. DataKind is probably one of the best-known global leaders. They essentially act as matchmakers, connecting volunteer data scientists with nonprofits and social organizations that need analytical help but lack the resources or expertise. They harness data science purely in the service of humanity.
And it's not just grassroots nonprofits, is it? The big tech players are getting involved too.
Absolutely. Many major corporations have recognized the power they wield and have launched dedicated initiatives. The sources mentioned several: WCO for Good, SAS Data for Good, IBM's Science for Social Good program, Teradata, Doing Good with Data. These aren't just PR exercises. They often involve significant investment in providing tools, training, and expertise to help nonprofits leverage data more effectively to scale their impact. They're helping organizations tackle complex problems like optimizing resource allocation for aid delivery or building predictive models for disease spread.
That's great to see. Are there national level efforts too?
Yes, definitely. The sources mentioned the Data for Good Foundation in Canada, for example, which is a national nonprofit, specifically helping other Canadian NGOs use their data better for community benefit. And you have platforms like Facebook Data for Good, which, while needing careful navigation around privacy, aims to empower partners with aggregated privacy-preserving data sets. For instance, using anonymized mobility data to help public health officials understand population movement during the COVID-19 pandemic response.
You know, this actually offers a fantastic opportunity for our listeners, for anyone interested in getting deeper into analytics. Getting involved in one of these community-based volunteer data for good initiatives seems like a perfect way to gain hands-on practical experience. You'd be working with real-world messy data, tackling complex problems, and at the same time, you're making a genuine positive impact. It's a win-win. Learn skills and contribute to something meaningful.
Couldn't agree more. It's a fantastic way to apply these powerful tools for broader benefit.
So what does this all mean? We've journeyed from just recognizing the need for big data analytics through understanding those crucial success factors, especially the non-technical, the cultural shift towards facts, then diving into the architectures.
Right. We've seen Hadoop offering that cost-effective, robust batch processing for huge data sets, while Spark delivers that incredible in-memory speed needed for iteration and near real-time analysis. And we've seen how stream analytics is becoming non-negotiable for acting on data in motion.
It really feels like the whole infrastructure of digital business and increasingly society has been fundamentally re-architected around these capabilities.
It truly has. The shift is profound, moving from a world where we carefully curated small amounts of structured data in warehouses to a world where we can potentially ingest everything and process it almost instantly.
Okay, let's leave our listeners with a final thought to chew on, something provocative building on what we've discussed.
Okay, here's something that comes directly from the sources, particularly around NoSQL and its trade-offs. We established that many high-performance NoSQL databases achieve their amazing speed and scale by consciously relaxing those strict ACID compliance guarantees, atomicity, consistency, isolation, durability that traditional databases uphold rigorously. Now think about this. As real-time data and immediate analysis become absolutely essential for more and more critical systems, not just e-commerce recommendations, but medical diagnostic tools, autonomous vehicle navigation, financial trading algorithms, the second-by-second optimization of public power grids. How much data consistency, how much absolute reliability are we as a society willing to trade away in pursuit of ever-increasing velocity and scale? What are the potential consequences of a system designed for maximum speed experiences, even a tiny transient data inconsistency at just the wrong moment? It's a profound trade-off between speed and safety that we're increasingly making, sometimes without fully realizing it. Something to think about.